Alright, so we're going to talk about the calculus of parametrics today. And the good news is that most of these problems are going to be very, very common sense. So if you want to find slope in terms of parametrics, you really just take dy dt, so your derivative in terms of time, or in terms of whatever your parametric value is, for y, and then divided by dx dt. And if you think about like multiplying by the reciprocal, it ends up being that the dt's cancel out. So that's really what you want to do. So if we wanted to find the slope of this set of parametric equations, you find dy dt, so 3 divided by dx dt. Remember, this is t to the 1/2. So drop down your 1/2, t to the negative 1/2, which ends up being, if we want to be, nice about this, divided by halves multiplied by the reciprocal, 6, and this ends up being t to the 1/2, or square root of t. That would be our derivative. And now, at this particular one, we're doing it at time equals 1, so the slope would be 6. Alright, so that's what you want it to be. You want to be able to do the derivative of y divided by the derivative of x. Now, one of the things you see here is our dy dt, dy dx, or our slope, is in terms of t. So when we do our second derivative, what a lot of people want to do is just do the derivative of this a second time, and we get our second derivative. The problem is we want to do our second derivative in terms of x, and this is not in terms of x, this is in terms of t. So what we have to do is the exact same thing. We take the derivative in terms of t of our y value, which is our first derivative, and then we have to divide that by dx dt. So it's not anything different, it's just that a lot of people want to do their second derivative by just taking the derivative of their first derivative. Well, that's fine. This is y basically. So for our problem, anytime you want to find the derivative of something, you take dy dt, so take dy dt, and then you have to divide it by dx dt. So it's more like we're taking dy prime dt divided by dx dt. People have a little bit of a problem with this because of the fact that they're thinking of this as being the whole thing already. So when we want to find our second derivative, we take the derivative of our derivative, which is what a lot of people want to do. So we drop down a half, so 1/2 of 6, so 3 t to the negative 1/2. And then we divide that by dx dt, which we kind of already know dx dt is this fun thing. So divided by 1/2 t to the negative 1/2. Alright, now that's a little bit of an awkward thing. So let's see here. We've got, this is really 3 t to the negative 1/2, so 3 t to the 1/2 up top, right? Okay. Oh, no, that should not be there. It's just 3t to the positive 1/2 on the bottom, be negative 1/2 on the top. Which actually, let's back this up a little bit. So trying to figure out what this should be, when we do that derivative, we usually put it on the bottom, but let's leave it as, drop down our half, which cancels with our 6, we get 3t to the negative 1/2. If we left it up top there, this would make things a lot easier, because now we're going to divide by dx dt. This t to the negative 1/2 ends up going away, and this whole second derivative just ends up being regular old 6. Alright, so the slope at the point would be 6, and the concavity would also be 6. Yeah, fun stuff. Now let's try this again. So we want to find dy dt, so we just take the derivative of y, which is 2, over the derivative of x, which would be 2t plus 3. That would be dy dx. It's our slope, and we want to do this at t equals 0, so we end up with 2/3 when we plug in t to be 0. Alright, that's fun stuff. Now, when we want the concavity, we've got to do the derivative of this fun thing right here. Alright, so that's the easiest way of thinking about that. A lot of people like to do the quotient rule from here. The 2 is just a constant, but the problem is you get this other 2 here and this 3 that kind of mess with it. You do it with 2 and then 2t plus 3 to the negative first. It might be a little bit easier to do it, think of it that way. So 2 is a constant. So this derivative, so we're looking for the second derivative, so d squared y dx squared. So we drop down the 1, so this would be negative 2 over 2t plus 3 to the negative 2, so squared, and then you guys still multiply by the derivative of the inside, which would be a 2. So times 2. So this ends up being negative 4. Alright, so that's our derivative. And then we got to divide this by the x dt. Okay, so just say 2t plus 3. Alright, so as far as that goes, we want to clear this up. This ends up, this is in the bottom. Anytime you want to divide a fraction by a whole number, this goes in the bottom. And you can make this to the third power. This is all this to the first. So we get rid of that on the bottom. And then, so that would be our concavity in general. We want to do this at t equals 0. And we end up with negative 4 over 0 plus 3 is 3 cubed 27. So you do dy dx divided by dx dt to find our slope. Our second derivative, the trick is you do the derivative again, but you got to make sure you divide by dx dt a second time. Alright, so concavity is a little bit tricky. Slope is really easy. Let's look at arc length. Arc length is possibly one of the easiest things that we'll do. Alright, so arc length in parametric form, actually we want to just go back to the distance formula. So the distance is the square root of x minus x squared plus y minus y. Now, we're talking about a small change in x, so basically like dx dt squared. Some small change in x in terms of some other variable time, that's fine, plus a small change in y, dy dt squared. Alright. Now, we did this one thing where we took out our, and there should be a dx here. I mean, we could start talking about the whole thing about how to figure out, you know, this is basically one small piece of arc in an individual position time. We want to add up all of these, so we end up basically getting the integral dt from t1 to t2. That's really it. It looks like the distance formula is the distance formula, basically. We're just doing this distance in terms of time. Alright, well, let's try to apply that arc length formula. It's one of the easiest things that we'll do. So we have an interval from -1 to 0. Okay, that's fun. Square root of change in x. So change in x is talking about derivative. So dx dt, so 2t squared, change in x squared, plus change in y, so plus 12t squared, and then just dt. And the funny thing about this is unless you have a very specific, like, sum or difference of squares in the bottom here, not difference of squares, but like perfect square trinomial somehow in here, this square root's not going to do much. This is calculator. So once you figure this out, then you probably want to type in your calculator 4t squared plus 144t to the fourth, just so that you don't have to worry about your parentheses too much. But from here, toss in your calculator, you get an answer. Same thing here. Integral from 0 to 1/2. And be careful that there's no vertical asymptotes, anything weird. Like natural log is not fine when you end up getting, I mean, basically t can't be bigger than 1 in this case, because you can't have natural log of a negative. And if you took 1 minus like 4 here, you have a problem. And that's why we're talking about on this interval. So you might want to make sure that your functions are defined, but you'll probably end up getting an error if you have some sort of vertical asymptote, or lim does not, or sum does not match, some sort of an error if this sort of thing can't happen. But really just trying to get at can you do your derivatives? So the derivative of x would be arcsine. Well, arcsine formula, 1 over the square root of x squared minus, 1 minus x squared. And then we got to square it. So what basically happens is the square root and the square cancel. Okay. Minus, and then easy way of dealing with this is take this half out front. You no longer have a square root. So we have 1/2. And then the derivative of the natural log, the derivative goes on the top, negative 2t over the original goes on the bottom, 1 minus t squared. And we got to square this. I can make the 2's go away. I can't make the minuses go away because this one has to be squared, but I mean technically it ends up going away anyway. But once we have this, we just toss in our calculator and we get our answer. Alright, now the surface of revolution is even easier than it normally is. We have our arc length. If you remember, for surface area, you had to figure out what the radius was. So we basically have our circumference, 2 pi r, times our arc length. Now, the good news is, if we're going about the x-axis, so let's say we have some sort of a function here. Parametric, we have dx dt, dy dt. The distance to the x-axis would be our y of t. That's really it. The radius to the x-axis, what about the x-axis, is y of t. The radius to the x-axis would be x of t. So if you remember from before, when we went about the x-axis, this was like our function height. When we went about the y-axis, this was normally just x minus the axis. Alright, just like regular old x. So for these, if I'm going about the x-axis, it's just y of t. Now if I want to go about like y equals negative 2, it would be y of t minus negative 2. Usually for parametrics they stay to the axes, but the good news is if I'm going about a horizontal line, I have a distance to a horizontal line function basically. Alright, let's see what we got. Okay, so for this one, all we got to do, we need a 2 pi. And if we want to go about the x-axis, we put the y of t. So t plus 2, sorry, keep it in the same order. We have some bounds, 0 to 4, and then square root of your arc length. So x prime, which would be 1/2 t squared, plus y prime, which would be just 1 squared, dt. The only thing that would change if I want to do the y-axis would be exactly the same, except this would no longer be the y, it would just be the x of t. So 1/4 t squared. Nothing else would change. This is generally not something you're going to be able to do by hand. It goes right in the calculator. That's it for surface area.